and welcome. This is lecture number 6 in the course on advanced power plant design in the fall of 2014. I'm Nicholas Seifert, and this lecture is going to be on mass transfer and CO2 separation through membranes. The goal is to give a quick introduction to membrane separation. After the midterm, we're going to be going into depth into all the different, the three main types of CO2 separation, which are membrane separation, and then separation using solvents and sorbents. Today, we're just going to get a quick introduction to it and introducing you to some diagrams that are going to look very similar to what we saw with heat exchangers. Here, the driving force for exchange is not temperature, but it's going to be the concentration. Is going to be the, so we're going to be saying Fick's law a lot in this lecture. So, as I said, so Fick's law is that the flux is equal to, is proportional to the diffusivity of the flux of species I. So in this case, normally I is the CO2. Though it could be for species that we don't want, let's say maybe nitrogen, right? So the flux of, so here we would say the flux of CO2 is equal to minus the diffusivity of CO2 times the derivative of the concentration of CO2 with respect to x. Right? So it's the gradient in the concentration that is driving a flux. So if you have a gradient in the CO2 concentration, then that can cause flux in the CO2. If we have gradients in nitrogen concentration, that can also cause flux of nitrogen to go through a membrane. Of course, in the membrane will have very, very different values for diffusivity for CO2 versus nitrogen. And of course, you'd ideally want to design your CO2 separating membranes to have extremely large value of CO2 diffusivity and extremely low value of diffusivity for hydrogen or nitrogen or other gases like that. So there are a lot of ways of building membrane systems. A lot of them look like on the left where you have these small fibers that go through. This is kind of like a shell and tube heat exchanger, except for everything is shrunk down in size. Or you could have large flat plates, as shown on the right, where you'd have flow going on either side. You'd have your one side there was your feed gas, which is then maybe your flue gas, your syngas, and then on the other side is what you're permeating through the membrane. Now I want to get a little bit of terminology clear on that we'll be using throughout this lecture. So there's four, and most of the time most membranes are run in counterflow kind of directions, where you have on one side you have your feed gas coming in, and the gas that remains on that side of the membrane is called either the retentate or the reject. Different people use that terminology differently. Sometimes it's called your clean gas, right? You have your feed, and then you might have your clean gas on the other side. Sometimes it's called the retentate, and sometimes the reject. On the other side of the membrane, on the same side as the reject is normally where you're sending in your sweep gas, and then on the side opposite the feed is going to be the permeate. And so those are the four main terms. So in a counterflow module, you have your feed and retentate. Feed is the input, retentate is the output. On the other side, your sweep is your input, and your permeate is your output. So just like we had in counterflow heat exchangers, we can draw what this looks like. Except for not temperature, we're going to be drawing the concentration. In particular, we're interested here in the concentration of carbon dioxide. So I'm going to be showing you these diagrams for both a post-combustion capture case, and then in the next slide in a pre-combustion capture case. So in the post-combustion capture case, we've got flue gas, and that's our feed. Our feed's coming in on the top right, and it's going to have a partial pressure of carbon dioxide of about 0.14 atmospheres. Okay, so from the partial pressure, because membrane processes happen at constant temperature, I'm going to be interchangeably using partial pressure and concentration. So when I say that the driving force is a gradient in the concentration, what I mean is the gradient is the gradient, that there's a gradient in the partial pressure, right? Because the difference here is just R times T. T is a constant. So Fick's law can be written as also the flux is proportional to the diffusivity times the gradient in the partial pressure, right? So we got a partial pressure of CO2 of 0.14 atmospheres coming in on the flue gas, and we need to capture 90% of the CO2. So that means the outlet of the flue gas, the partial pressure, has got to be down on the order of 0.02 atmospheres. Okay, that's a significantly small number. So the question is, of course, how are we going to do this? And so that means we also need a gradient of concentration through the membrane, or else we'll never get any flow. So that means the partial pressure of CO2 on the pure side, or what we'll call pure, depending on whether or not there's a sweep gas, is going to have to be really, really, really small. If you had no sweep gas, the concentration on the pure CO2 stream would have to be less than the lowest pressure, which is on the feed side, which is in this case about 0.02. And in that case, you would have a straight line at the bottom here, and so if your lowest partial pressure on your in the reject, so on the retentate, just as it leaves, if that's 0.02 atmospheres, if you had a pinch point constant pressure, partial pressure gradient of 0.01 atmospheres, that means the highest the partial pressure would be on your pure side would be 0.01 atmospheres, right? Which means we now have a lot of work that's going to be required to compress CO2 from 0.01 atmospheres up to 150 atmospheres. Absolutely huge number. So there's a couple things you can do here. You could sweep with steam. So if you sweep with steam, what it will allow you to do is it will allow you to have a slope in the bottom line here. Okay, and you can have it such that that line will actually at the entrance of the sweep, there's no partial pressure of CO2. So that line can go all the way down to 0.000, which means the pinch point partial pressure difference on the left side of this is about 0.02 atmospheres. Not a very large number, but it's greater than 0. And then what happens is as the CO2 crosses over, the partial pressure increases, and we can have it increase. We could have it increase as high as 0.14 atmospheres. Probably a more realistic number is about 0.05 atmospheres. So what this means is that we have still a fairly low pressure CO2, and we still have a lot of work. But at least with the ability to put in a sweep of steam, it means we're already a little bit closer to 150 atmospheres than we would be if we didn't do the sweep and we're at 0.01 atmospheres or below. And as a reminder, when you're using a compressor, it's the log of it's the logarithm. The amount of work is proportional to the logarithm of. So if we have to get to 150, it'd be the logarithm of 150 divided by the starting pressure. So if we can start at 0.05 atmospheres, that's a lot better than starting at 0.01 atmospheres. It's like logarithm of 5 better. Now I want to switch gears and talk about for precombustion. Precombustion is when you have a gas that's a mixture of hydrogen and carbon dioxide coming from a coal gasifier. In this case, the total pressure might be around 50 atmospheres, and the partial pressure of CO2 in the inlet feed gas is about 20 atmospheres. You can see we're already at a much higher partial pressure. So to do 90% capture now, the retentate, the partial pressure of CO2 in the retentate is about 2 atmospheres. And then what we'd likely do is, once again, we would sweep with some steam, or maybe or something like steam. The reason I've been mentioning steam here is that you can now cool off the gas and the steam will drop out, leaving you with the full total pressure being then the carbon dioxide. So that's one nice thing about sweeping with a gas that can condense out after you cool it. So here what we'd be doing is we'd be sweeping with steam, and so we could have the inlet pure CO2 stream be some number between 0 and 1 atmosphere on the sweep side. And if you were sweeping gas at a pressure between 5 and 10 atmospheres, you could have your partial pressure of CO2 exiting and be on the order of 5 atmospheres. And then when you condense out the water, you could, that partial pressure, of course, would increase. So we have a system now where in this pre-combustion one, before we've done any work, we already have partial pressure of CO2 between, let's say, 5 and 10 atmospheres. That's a lot better than the case before, where it was some number between 0.01 and 0.05 atmospheres. We're a lot closer to 150 atmospheres. And this is one of the reasons why CO2 capture from pre-combustion streams has a very low levelized cost, meaning if there eventually is a tax on CO2, one of the first places you'd see the CO2 capture implemented would be from pre-combustion streams, and that could be either from coal gasifiers or natural gas reforming. Natural gas reforming is often used in the production of fertilizers like ammonia. So that's where you'd be seeing this stuff occurring first. Now I want to point out, just as we did for heat exchangers, you can calculate the area of the membrane. This is the amount of membrane area that you need to get a certain n dot separated, so a certain flow rate of CO2 separated. And just as in the heat exchanger case, right in that one, we had A was proportional to Q dot over LMTD. This time it's proportional to the n dot divided by LMPD, the log mean pressure difference, where the log mean pressure difference is effectively defined the same as for the temperature. Just remember that it's the log mean partial pressure difference. I didn't put LMPPD so that it would look like the LMTD. Right? But remember, this is the partial pressure of CO2. It's the driving force on the left side of the membrane, and then minus the driving force on the right side of the membrane, divided by the logarithm of the driving force on the left side, and divided by the logarithm of divided by the partial pressure gradient on the right side. And then the other thing I want to point out here is that inside we have 3 resistors to mass transfer, just as we had in the heat exchanger. In the heat exchanger, we had to exchange heat from the fluid phase, hot fluids phase, to the wall, and then through the wall, and then finally the third resistor was heat transfer from the wall to the cold fluid phase. Well, we're going to have the same thing happening here. So I've given the example for a post-combustion membrane case where on one side you have CO2 that needs to diffuse from the nitrogen. It's got to go through a membrane, and then finally it's got to go from the membrane wall into the water vapor. And in that case, if your membrane, if there's a characteristic length D, which is like the diameter for the membranes, then inside the bracket here, your mass transfer resistance is, for the first resistor, is that distance, right? As you can imagine, the resistance increases with that distance of the diameter, and then we have an RT. Then we have then we're divided by the Sherwood number, and the Sherwood number is exactly the same in the analogy. It's the same as the Newton's number, so it's equal to 4 for laminar flow, and then when you're in the turbulent regime, it's going to go like the Reynolds number times the equivalent. This time it's not the Prandtl number, but there's another equivalent non-dimensional number that we'll be covering. And then we're going to be dividing by the diffusivity, right? So resistance decreases as the diffusivity increases. So that's the resistance on the feed side. And then we're going to be doing the resistance through the membrane is called 1 over P star, where P star is the permeance of the membrane for CO2. And that will be given to you in problems. And then finally what we have is we have the mass transfer resistance on the sweep side. And note that if you have no sweep gas, then this term will drop to 0. So if this is a gas, I want to point out that the diffusivity of A into a bulk gas B, so DAB, there's an equation, just like we had for the somewhat related to the equation we saw for viscosity, but it's slightly different. This equation is DAB is given in units of meters squared per second. When the temperature is in Kelvin, the total gas pressure, that's P sub T, make sure that it's the total gas pressure that matters in this equation. In earlier equations we saw it was the partial pressures. So here, if gas pressure is in atmospheres, if the cross section is given in angstrom and the molar mass is given in grams per mole. I want to point out here that sigma sub D is very closely related to the sigma sub mu that we saw for viscosity. It's a collision integral, and it looks like the collision integral, except for just there's a slight offset. So it looks like 0.1 plus 1.1 divided by x sub d raised to the 0.5 power. Here x sub d is the temperature of the gas divided by the Leonard-Jones well depth. So in that equation, there's a sigma AB. I want to point out that sigma AB is equal to the Leonard-Jones well thickness of A plus the Leonard-Jones well thickness for B divided by 2. And the Leonard-Jones, so epsilon AB is the Leonard-Jones well depth, and that's proportional to the geometric average of the well depths. So the first one is arithmetic, the sigma is an arithmetic average, epsilon is a geometric average. Here are values for the main species of interest in this class. The Leonard-Jones well depth as well as the Leonard-Jones size. The depth is given in Kelvin. Right? It's really an energy, which is kind of, you can always turn into Kelvin through like the Boltzmann constant. And then the Leonard-Jones size is basically the kind of a characteristic size of the molecule. I want to point out here the Leonard-Jones depth is largest for water vapor. And then, as I mentioned in the previous course, water vapor has this unique, it's the only one that I'm aware of, that epsilon that you're going to use either when calculating diffusivities or viscosities. Remember, thermal conductivity was calculated from the viscosity. So what's very interesting is that the value of epsilon you use in those equations is different, and it's only for water vapor, and it's likely just because of the water vapor is the only polar gas that that is shown here. The other ones are either nonpolar or virtually nonpolar. And so just be careful when you're using epsilon d. Epsilon d is much smaller than epsilon mu. Now sigma for water is the same, but for epsilon it's slightly different.